No, just kindly 1 minute. Principal is joining, please.
No problem, no problem.
YouTube இருக்காங்களா மேடம் இதுல?
Good morning, sir.
Good morning, sir. Sir, good morning. Good morning, sir. Welcome, sir.
Good morning. Good morning.
Good morning, sir. Good morning, sir. Good morning.
Good morning, sir.
Good morning, sir.
Good morning.
Rangasamy, you can start, ma'am.
Okay, we'll start, madam. Okay.
Shankar sir, you can go for YouTube live streaming. Okay.
I just started recording.
Rangasamy, you can start.
Okay. Good morning, everyone. Myself, Rangasamy from Department of Chemistry. Today we have assembled through online to listen the lecture on Introduction to Thermodynamics. Actually, this topic is very much essential to understand the need of thermal energy in our day-to-day life. So first of all, I would like to thank Professor Arnab Mukherjee for accepting our invitation. And I thank our beloved principal, Dr. M.G. Raghunathan, for his gracious presence. Now, let me call upon Mr. Anand to compare the program. Anand?
Good morning to all. I, Anand C., an element from the Department of Chemistry, Guru Nanak College, welcomes you all. We, the Chemistry Association of Guru Nanak College, Chennai, organizing a 2-day national webinar on Introduction to Thermodynamics. Thermodynamics is all about energy, how energy gets used and how it changes from one form to another. Refrigerators, deep freezers, air conditioning systems, fossil fuel streams are all related to thermodynamics. So, now I would like to call upon the enthusiastic energy source of our college, Dr. M.G. Raghunathan sir, Principal, Guru Nanak College, to deliver the welcome address. Sir, please.
Good morning, all. That was a nice introduction about a principle. That's why I am excusing him. The esteemed resource person of the day, Dr. Arnab Mukherjee, Department of Chemistry, my dear colleague and BTN Research Department of Chemistry, Dr. Velachery, my dear colleague, my dear beloved brother, Dr. Rangasamy, and my colleague, Dr. Saroja, Mrs. Saroja, and Dr. colleagues who are here. Again, chemistry department, as I told you earlier, also it is unique in all the assignments which they do. Interaction thermodynamics. I don't know, so far I was thinking about that. This is a topic in physics. Now I am going to learn about how this thermodynamics is related to chemistry also. Because as usual, plus 2 we used to study BSc physics, plus 2 physics, chemistry, maths and biology. And my allied subject is BSc chemistry. So that much interest I took over, but little maths, I could not get my BSc degree admission in my college. Though somehow I came to zoology. Again, now I am going to learn about Thermodynamics through Professor Arnab Mukherjee. In that way, sir, a hearty welcome to you to Guru Nanak College, sir. And you people should come to college in the non-offline. You have to visit our campus. Guru Nanak College takes the pride of inviting you once again to the college offline seminars. Because nowadays I could see all the departments are wonderfully arranging, and I could see that much eminent persons are there in the lists of chemistry department. Why can't we all meet together? If the normalcy comes back, we have to meet, sir. We have to meet, and we would like to utilize your resources, expertise in these particular subjects, so that it will be benefit for all the students. So once again, I welcome you, sir, and my best wishes and congratulations to Dr. Velachery for arranging a wonderful program. Probably, madam, you have a wonderful team of supporting the research team. I understand under the dynamic research interest of Dr. Rangaswamy and other colleagues, Dr. Noor Jahan, and you have a wonderful team. Chemistry department, as usual, leads the Sir?
Seconds, I could not hear you.
Okay, probably
Hello.
example.
Can you hear me?
Yes, sir.
Yeah.
I think he has not heard anything.
Hello.
Sir, hearty welcome to you, sir. Sir, can you hear me?
Hello, I cannot, it was fine, but now I cannot hear you. Okay, if you can hear me,
Yes, sir.
then maybe you can write in the chat that you can hear me.
Sir, we are able to hear you. Can you hear me? Dr. Arna? Madam, Dr. Velachery, can you hear me?
Yes, sir. And
Yes, sir. Yes, sir.
Okay,
But your voice
I cannot
breaks,
hear
sir,
you,
that's
any
why.
of you. So, if you else can speak,
I have
so
posted
that I
also.
know that
I can.
it's not
I think
no,
you
I
can
cannot
hear
hear you,
Dr.
Dr. Velachery also. So it may be my speaker. Just 1 second. So that
So,
was
madam, maybe some technical.
few minutes back. Hello. No, that is also not there. Okay. I'll just enter again after leaving.
Okay, madam, anyway, I have done my job. I may convey my regards and wishes to him.
Thank you so much, sir. Thank you so much.
Thank you, sir. Thank you. Thank you, sir.
Already, some few other visitors are there in my room itself.
Okay, sir.
Thanks for the opportunity to me.
Thanks a lot, sir.
My best.
Anand?
Okay, sir. Thank you.
Anand?
Thank you so much, sir, for the inspiring and encouraging words. Now, I would like to call upon Dr. R. Rangaswamy, sir, Assistant Professor, Department of Chemistry, Guru Nanak College, for the introduction of resource person for this webinar.
Rangaswamy,
Okay, let us wait for some time. Okay, let him come.
Rangaswamy, let the resource person join. He has joined now.
Yes, madam. Right.
Dr. Arnab, can you hear me now?
Now I can hear you.
Yeah, thank you.
Okay,
Rangaswamy, you
good.
can proceed now.
Okay, good. Okay, madam. Okay. I find immense pleasure in introducing our resource person, Professor Arnab Mukherjee from Indian Institute of Science Education and Research, that is ISER, Pune. Professor Arnab Mukherjee did his BSc from Jadavpur University in 1998. As an integrated PhD student, he then did his MS in Chemical Science and subsequently PhD in Theoretical Chemistry from the Indian Institute of Science, Bangalore in 2005. He went to École Normale Supérieure, Paris, France for his first postdoctoral research, and then the University of Colorado Boulder for the second. He joined ISER Pune in 2009 as an assistant professor. From the current year onwards, he is serving as professor in ISER Pune. Dr. Mukherjee works on computational chemistry and biophysics, primarily involving classical mechanics. His primary research interests are drug DNA intercalation, protein folding, structure, dynamics, and thermodynamics of liquids. Development of new methods such as single water entropy, drug design, local surface curvature, DNA structure prediction from sequence, etc. Professor Arnab Mukherjee has published more than 60 research articles in reputed high-impact international journals. He has been invited to deliver nearly 20 lectures in the national and international conferences in India as well as abroad. With this brief introduction, I invite Professor Arnab Mukherjee to deliver his lecture on Introduction to Thermodynamics. Please, sir.
Okay, thank you all. Thank you for the invitation. Thank you, Professor Raghunathan, the principal, and also Dr. Illarasi, who actually contacted me to give this lecture. So it's my real pleasure to talk to you or give this particular class lectures. Normally, we give research seminars everywhere, and there are very few opportunities to, give talk on class topics. So after joining IISER Pune, I used to teach statistical thermodynamics for MSc student here. But then after some time, 2014 onwards, I have been teaching here first year students the basic thermodynamics and also basic quantum chemistry. So again, I moved that, away from that, but my teaching to the students helped me to learn the subject, and also that helped me to launch the NPTEL course. You can all see the name of the course is Chemical Principles 2, but also later on I changed the name to Basic Thermodynamics, Classical and Statistical Approach. So so just wanted to know that, am I clearly audible, or is there any background noise or anything?
Yes, sir, it's audible and very clear.
Oh,
yes,
okay, great. So I'm now going to, I'm just going to share my slides now. So typically, the NPTEL course that I have, I urge all the students to, look into that and get some time to, it's free, of course. The contents are there, and a lot more material you can find there compared to what I can do in 2 days. And mostly my slides here, what I'm going to show, are from those NPTEL slides only. And I can assure you that you will find something new, something interesting in that lecture, which you normally may not find in other books and standard books and standard references. So right now the knowledge base is really high. So for example, if anybody wants to study any subject from any part of India with the help of a mobile phone and some 4G network, one can really learn any subject that one wishes to. And I urge my students always to keep learning new things, because that gives us much more pleasure than what we can actually get from many other things. And you will realize that only when you will start learning things that interest you. That is also very important. What interests you and what doesn't. So if you find your interest, don't hesitate to look into internet and first find out the best possible course. The feedback and other things will help you to find that, and then follow the course. And since there is no pressure of exam, no pressure of any evaluation, learning will be much more fun, I guess. So with that, I'll just start today. Remember, I will have to go a little faster, and because I have to cover minimal thing. So let's see how it goes. So today I will talk about mostly classical thermodynamics, classical part, which is normally taught in undergraduate level. But tomorrow I am planning to talk about statistical aspects of thermodynamics, and both are interconnected. Without understanding one, other one is actually a little bit difficult to understand. Okay, so I apply thermodynamics in my research work, because when I talk about, let's say, drug DNA intercalation, like anti-cancer drug which goes into DNA, I talk about binding, and that binding is governed by free energy. So therefore, understanding thermodynamics helps to understand those processes, biophysical processes, which are important also in more detail, in atomistic or molecular detail. Okay, so I will just share my slide now. Okay. So if I want to share my slide, I can share my screen. That is not a good thing. There is a background noise.
Okay.
Okay. Yeah. So okay. So I'm just trying to find. I got it. Okay. So I'm sharing my slides now. Okay. So can you see my screen? Any of you can say? Can you see my screen now?
Yes, sir.
Okay. Great. Okay. So we'll start. So thermodynamics. So basically, thermodynamics is about understanding heat, energy, and work. So typically, people talk about the definition of thermodynamics.
The screen is only blank, dark.
Is it okay? Okay. Is it okay now? Is it black or still, or it is? It's still black. Okay.
It's still black only.
Okay. Okay. Just one second. I will try to share in a different way. Then let's try to share my entire screen, and then see if it helps. It helps. What about now?
No, sir, not yet coming.
Okay. Okay,
Yes,
so
sir,
now it has come,
yeah.
I guess, right?
Yeah, yes.
Okay. So I'm now making it full screen. It is still okay?
Okay, sir.
Okay, great. Okay, so thermodynamics is about heat, energy, and work. We know about this particular term. People normally talk about thermodynamics as thermo means heat, and dynamics is like, movement and all that. But I want to describe it in a little bit different way. So as you can see that this is exchanging between heat and energy. So they are basically, exchange with each other, and work also. This particular animation shows that they're interconnected, heat, energy, and work. And there is this envelope of entropy that kind of governs whether there will be a change or not. Okay, so again, there are information that I'm going to skip. I'm sure that you'll find it in many places. But let us talk about this. So here, what I'm trying to show here is, the distribution of energy. So P is probability of energy with respect to energy. So this is called histogram or distribution. So you see in the first plot, the distribution is narrow. And in the second plot, the distribution is bigger. So let's say you have some amount of energy that you want to distribute, or some amount of money that you want to distribute among few people. So if you give all the money to one person, then the distribution of money among people will be very narrow. And that is the first one. But if you distribute it, let's say equally or more evenly, then this will be the next distribution. Given the same amount of energy or money, the distribution determines whether the entropy will be high or low. So if you understand this particular slide itself is enough for the rest of the lecture. So energy is a property of matter. That means if I have a glass of water, I can calculate its energy from quantum mechanics. Or if I have a molecule, I can calculate its energy from quantum mechanics. But whether that molecule will react and make something else or not, that will be determined by entropy, which again is distribution of energy. So when I have a coal, let's say I have a piece of charcoal, the energy is concentrated at charcoal. If I give it a small spark, which is basically a kind of a catalyst, then it will burn, it will produce carbon dioxide, and it will produce heat, and it will go everywhere. So the concentrated energy in the charcoal has now gone everywhere, increasing the entropy. But the energy is conserved. That has not changed. We did not produce new energy by that. We did not deduct any energy by that. So energy is conserved. Or you can think of money being conserved, but it has now been distributed more evenly, increasing the entropy. So at the end of the day, a flatter distribution, a more even distribution has higher entropy, a more narrow distribution of energy has low entropy. So this is enough to understand thermodynamics, in my opinion. However, we have to go through the process of defining things, giving notations, learning that what we call what, and then only we'll come back to this again, maybe tomorrow, and we'll discuss this distribution back again. So thermodynamics is everywhere, omnipresence. Why it is everywhere? Because thermodynamics deals with the change. It is not about, as I said, it is not about a particular system. It is about change of a system, change of matter. So change of matter can happen through chemical reaction. Change of matter can happen, in terms of conversion of energy from solar energy, for example, I can get heat energy, or from electrical energy, or chemical energy, or mechanical energy. So the conversion will keep on happening. When you, power a car, or you drive a car, you use chemical energy to convert to a mechanical energy. But when you, use a dynamo, then you use electrical energy to convert to mechanical energy to convert to some other energy. So, or chemical energy in a dynamo to convert to an electrical energy through mechanical energy. So it's all conversion, and each conversion will have a penalty to pay. Each conversion will increase the entropy of the universe. In fact, you will see that everything that we do, every action that we take will either increase the entropy or entropy will remain constant, but mostly it will increase the entropy, because there is a change associated with that. Change is also there when we change the phase of a system. For example, you take ice and convert to water. Essentially, we are not really changing the matter at all. We have same amount of ice, same number of water molecules that were there in the ice is converted to water, let's say. But there is a change of phase, and that requires energy and of course entropy penalty. And then let's say, it becomes vapor. So every changes will be associated with a change in energy, a change in entropy. Energy is conserved if you do it in a proper manner, or energy is conserved anyway for the universe, even if you do with whichever way you want to. Change of heat to work, as I already discussed that, and combination of all that. So thermodynamics is a subject to understand whether there will be a change or not. That is the bottom line. So in physical chemistry, there are two very important subjects. One is quantum chemistry, another is thermodynamics. Quantum chemistry will help you to, understand what is the energy of the system. You solve either in a particle in a box, or a hydrogen atom, or a hydrogen molecule, oxygen molecule, whatever, and you will get the energy of the system. But let's say I give you the energy of the system, and you have to tell me whether there will be a change or not. For that, you need to understand thermodynamics, or essentially entropy, because that is the gateway. That is the Darwan of with or basically God of the change. It will dictate whether the change will happen or not. So I'll talk more about that. So there is if you have read Lord of the Rings, there I normally there is a statement called there is one ring to rule them all. So here I just change a little bit and say that there is one rule that allows all change. And that rule is the rule of thermodynamics. Okay, so for some examples, we know all of that photosynthesis example where sunlight produces something that actually we can consume in our body. And when we are, it's a two-step process, right? So sunlight will convert to something like a, chemical energy which is stored in glucose, and that gets burned through respiration and stored in our ATPs. And those ATPs actually are energy currency of our body. Those ATPs will break ATP is adenosine triphosphate, right? So that's a high energy molecule that gets broken into AMPs, and that gives us energy for our body functions. So basically sun, you can think of that as a source of most of our energy that we use every day. So we don't produce anything new. It's all there, all there within our universe, and especially even in our solar system. Now, whatever we see, whatever you observe in around us, starting from organisms and plants and buildings or whatever, you can break them into atoms and molecules. Actually, atoms. So, for example, here I'm showing that a human being to broken down to organ systems, tissues, cells, organelles, DNA, molecule, and even at the end it will be just atoms made of carbon, nitrogen, phosphorus, sulfur, and oxygen. So when you observe something in a macroscopic world, that means the world that we can see through our eyes, we don't need a microscope or anything, that's called macroscopic world. Whatever we see in a macroscopic world, there are underlying microscopic things happening. Atoms are moving, molecules are moving, they're acting, and because of that, all the functions that we do or that we observe, they are essentially movements of those atoms and molecules. So wiggling and jiggling motions, that's what Feynman said. You see this cartoon example of a protein, a kinesin protein that is being transported beautifully along the microtubule. So this is a very famous video. It's called Happy Walk or something, but correct. The point is that it is that the molecule is actually walking, and this work is a work, and that work requires energy. We know that work is nothing but energy. Heat is nothing but energy. They're all energy. It requires that energy. And this work, when its energy is spent in that, there is also a penalty, which is entropy, which actually hits our body. Our body radiates those energy to the universe. Every day, we increase the entropy of the universe just hitting the surrounding of us. Now, another famous example is our vision. When light, so how do we see? When light falls on an object and that comes to our eye, we will be able to see that, right? But when light falls in our eyes, there is a chemical change that happens. A chemical change is basically an photoisomerization process. So this becomes cis retinol becomes trans. And cis to trans isomerization process that happens, it requires only a certain frequency of light. And that frequency is, we call it visible range. So if it is ultraviolet or if it is infrared, that means infrared is lower than visible range, ultraviolet higher than visible range in the frequency limit, we will not be able to see. That's why we can see only red to violet. We cannot see a light with frequency higher than violet or a light with frequency lower than red. We cannot that because this isomerization will not happen. So our body is constructed that way. So when you see, it is actually a reflection of a chemical reaction that happens with the help of energy. It will dictate whether it will happen or not. It will have so if we give entropy penalty, and even if we have an excess, yes, process will happen. So thermodynamics determines those changes. That's why this is so important. These changes I already talked to you. So continuously we see that water becomes vapor, and then again brings falls down as rain, and then in the colder atmosphere become ice and all that. Another example is carbon, graphite, and diamond, and carbon soot. They are all same. They are called polymorphic system. So same carbon is arranged in a different way to give rise to diamond or a carbon soot or a graphite. Same carbon atoms, you can break it down to carbon atoms. So these phase changes or this polymorphism also will be dictated by principles of thermodynamics. And most importantly, our universe in which we live in, people used to believe that the universe started from a point, solely a particular point at the time of Big Bang. So our universe is 13.7 billion years old. So before if I go back 13.7 billion years, the universe used to be a point. And from that point, it has expanded. So at that point, there was no universe. It was a point. There was no matter at all. It was only energy. And that energy got converted to matter. First, hydrogen and helium were formed in 300 million years or 400 million years, right? And then many other things happened, and matter got formed. And those matter that we see, our table, chairs, human beings, trees, seawater, normal, so everything that we see around us, which we feel as matter, they got formed from energy. So universe started with energy only. So this whole process increases the entropy of the universe. So the entropy was supposed to be okay. Anyway, the Big Bang theory may have still evolving theory. It may be correct or may be wrong, but that is right now is the belief that it started from a point. But again, there are doubts about that because nobody can see very near to that Big Bang time. But anyway, the point is that as the universe is expanding, entropy is increasing. And as it is expanding, the entropy is increasing, and it is increasing till today. Okay, I wanted to skip that because it was not part of that. Okay, somehow my changes are not here, but that's okay. Okay, so before I proceed further, these are the books that one can follow. Sylvia is a very good book for thermodynamics beginners. Atkins, of course, is a fantastic book. Hansen and Green is a very recent book that will give you the molecular aspect of thermodynamics. So name itself is molecular thermodynamics. Deal is another great book, and Callan has a very different approach of thermodynamics, very different from many of the other things. It is more mathematical, but it is beautiful. So in my course, normally I combine all the different things. Callan's approach, which is more mathematical. These two are statistical thermodynamics, and these two books are basically, you can have both classical and statistical thermodynamics. History. So thermodynamics is not developed by one person. Unlike, you can say quantum mechanics, very few. Schrodinger's name will come into the picture. Of course, some other people also contributed, Max Born and other people. But thermodynamics is, got developed for a long time. As you can see, like, 485 BC by Parmenides, so it says that there cannot be any vacuum present. Or then everybody contributed. Galileo, Torricelli, Vedic. That time their main aspects was to use vacuum pump and vacuum to do some work and things like that. Bernoulli again contributed enormously, and then from this Thomson onwards, and Carnot, Joule, and Clausius onwards, the thermodynamics that we study, classical thermodynamics, that was in that year, around 1800 to 1860 or something. This range, this 4 people. So they contributed to that, although Maxwell and Boltzmann contributed to the statistical aspects of thermodynamics. You see the time, 1872. By the way, 1872 was before electron was discovered in 1894. So that time people knew about atoms, but they thought that atom is the smallest particle possible. They did not know about electrons, protons, neutrons, or subatomic particles like gluons and mesons and other things. So that was the time when you can only know about atoms. This guy, Ludwig Boltzmann, developed a fantastic theory of thermodynamics from atoms and molecules, which contributed in finding out the Planck's constant. And that gave birth to quantum mechanics. It is that beautiful. Okay, so we can have more discussion on that, or you can see in my NPTEL lectures also. But while thermodynamics was being developed, a lot of people tried to find out a machine that will run forever. Isn't it wonderful that if you have a machine that doesn't require any energy, you have a fan, you don't want to give any bill, the fan will keep on moving in one direction. And you will don't have to pay any money for that. No electricity bill. And if that is possible, then slowly we can make machines that will do all our job without any energy. But that is not, thermodynamics says that is not possible. A perpetual motion machine is not possible to be built, because in order to get work done, you need to pay some energy, because energy is work. That's the first law of thermodynamics. So this racket was designed in such a way that it can only move in one direction, because if it tries to move in the other direction, it will get stopped. You might think that if at all it moves, it has to move in one direction, and that gives you some free work. But you will see that it is not possible. So it will violate first law of thermodynamics. And then there is another one, I probably will discuss that later on, which is called perpetual motion machine of the, just one second. I just wanted to see why it is not synced properly. Why it is not synced. 1022, it must be synced. Okay, fine. Okay, I am here. Okay. Okay, just one second. Yeah, I think it is coming now. I hope you can see my screen, right? Okay, anytime you can basically stop me and ask questions if you have any doubts. So is my screen visible? Hello?
Yes, sir. Yes, sir.
Okay, fine. Okay, so
But only the PowerPoint screen is not visible. The entire screen is visible. Now it is okay.
Now it is okay, right? Okay.
Now it is okay.
So yeah, so when you talk about thermodynamics, as I said, that we need to define some rules. Okay, because anything that we want to do, we need to define its boundaries and rules. Any game also, when you play a game, for example, cricket, we need to find some rules. We cannot bowl from very far or very close. We cannot throw a ball. We have to move our hand. So whatever, let's say kabaddi or hockey, whatever game you play, you need to define its rules. So when you play with thermodynamics, you need to define its rules. And those rules are typically the variables and the system. What is a system? System is something that we decide to work on. It can be a glass of water, it can be a bottle of water, it can be our whole universe. And so what is surrounding? Rest of the universe. And by that I mean rest of the real physical universe. Of course, the boundary is the boundary between them, but it's obvious from that, right? So let's take a bottle of water. The bottle of water is our system, a plastic bottle of water, and this is the picture of the early universe. So I am showing that to emphasize it's not, of course, to the scale. Bottle cannot be as big, right? It is not up to the scale, because then you will not be able to see the bottle. But the point is that except that bottle, everything else is surrounding, everything else. So system plus surrounding is our physical universe, actually. So we know about system, and there can be three different types of systems. Isolated system. A good example is a very, very good thermoflax where hot water will remain hot, cold water will remain cold. Of course, no system can be as isolated. No system can be fully isolated. So even if you buy a very sophisticated thermoflax, it might keep your tea hot for 10 hours or 12 hours, but eventually it is going to get cold. That means energy is leaking. But isolated system, no energy should leak, and it should remain at hot liquid forever. Then only it will be isolated, right? So in isolated system, your number of particles, volume, and energy are always same. Closed system. Closed for what? Closed for mass, not for energy. So plastic bottle is an example. So water is not going to evaporate out of this, but if you bring in a bottle from a fridge and keep it outside, it is going to get hotter and come to the normal room temperature. Or if you pour hot water here or tea here, it is going to get cold. So energy is being exchanged, but the amount is not changing. So number of particles is same. Temperature is going to be fixed. And the volume is, of course, going to be same. So NVT system is a closed system. And what is open system? Open system is an open bottle. The water molecules are going to go evaporate. So if you place a bowl of water outside, after a few days you will see it is dry. Why it is dry? Why the particles have evaporated? Isn't water more stable than a vapor energetically? Because water has hydrogen bond. Vapor will not have hydrogen bond. So water is more stable energetically compared to a vapor. Yet you will see that the bottle will become dry after a few days. Water is going to evaporate out. Why? Again, that is because of entropy. We'll come to discuss that. But open systems are systems where mass also can change and energy also can change. So if energy gets exchanged, temperature becomes constant. When mass gets exchanged, the chemical potential becomes constant. So these are the three different systems that normally we work on in thermodynamics. But variables, what are variables? I said macroscopic variables. Macroscopic variables mean the variables that we can actually measure by macroscopic instruments. For example, I can have a measuring cylinder and measure volume. I can have a thermometer and measure temperature. And of course, number of water we cannot measure, but we can measure pressure, and that way we will be able to also know the other thing. So macroscopic variables means when I go to a store and ask for a bottle of water, what do we say? We say that 1 liter bottle, normal temperature. That's what we say. So what are the variables we said? We said 1 liter bottle, so volume we said. We said normal temperature, so T also we said. And of course, atmospheric pressure is 1, that will determine the N already. Because if you say pressurized water, that will be a different N. But you need to specify 3 variables. 3 variables will determine the state of the system. That is the macroscopic variable. What is microscopic variable? Microscopic variables are not measurable without any instrument. Even with instrument also it is not possible always. Microscopic variables are positions and momentum of all the particles. So you need to specify for a 1 liter bottle there are 55.5 moles of water, which means there are 10 to the power 25 variables, that is 10 to the power 25 molecules. Each molecule will have x, y, z positions and px, py, pz momenta. So therefore, you will have so many variables to specify in order to specify that system. So those are microscopic variables. You only need position and momentum. And macroscopic variables, you will need these macroscopic ones. Okay. So, and of course, extensive and intensive variable, we all know that volume, if you add 2 volumes, it will become double. But if you add 2 temperatures, it is not going to increase. So for example, I'll rephrase myself. If you take a glass of water at certain temperature, another glass of water at a certain temperature, mix them together, temperature is not going to change. If initially the same temperature is not going to change. But if you take a glass of water and then another glass of water, it will become double glass of water. So this is extensive variable and these are intensive variable. Intensive variables do not change. And typically they are ratios of 2 extensive variables that I can discuss later on, or you can see NPTEL lectures for that. What is equilibrium? Thermodynamics is a subject of equilibrium properties. That is very, very important. I start a reaction. I cannot describe my thermodynamic properties when the reaction is going on. I can only describe after reaction is complete. So let's talk about binding of 2 protein. I can describe before they bound and once they were fully bound. But I don't know, or I cannot understand what is going on during the process, because that will require non-equilibrium thermodynamics. So equilibrium thermodynamics is the thermodynamics that we study, which means that a system is in equilibrium when there is no visible change happening during the course of observation. I look at a building and I find it is in equilibrium because I don't see any changes in days. But if you wait for 1,000,000 years, you are going to see change. So which means that the course of observation also is very, very important. Without this course of observation, you will see everything is non-equilibrium because everything is changing. But the scale, rate of change is very different. So depending on the rate of change, which is not topic of thermodynamics, that's a topic of chemical kinetics. But during that course of observation, if the rate is very slow, then less than that, for example, something changes over days, then within that day, it is in equilibrium. No visible change is going to happen within days. So if I take a glass of water, open glass of water, it is in equilibrium. But if I observe it for 10 days, it is not in equilibrium because water molecules are going to evaporate out and I'm going to see a change. So very important, these both the things, no visible change and course of observation. So although macroscopic variables don't change in the course of observation, microscopic do change. So a bottle of water, it looks the same for let's say 1 hour. If you observe for 1 hour, it looks same. There is no change. But microscopically, it changes every femtosecond or every picosecond, I would say, because particles are changing their positions and momenta at every picosecond or every femtosecond, in fact. But picosecond, I'm saying because in picosecond, it will move by its size. So this is the picture of those water molecules. They are changing all the time. So when I visualize water molecule, a glass of water, a bottle of water, I visualize water molecules there. And I visualize how they're changing. I used to have a movie here, but it's not. So now, let's talk about laws of thermodynamics. So as I said, that 1859, 1857, the Clausius came. So second law of thermodynamics was first to be introduced. Then came the first, and then came the zeroth law. Why it is zeroth law? Why it is not a fourth law? It came later. Because without zeroth law, none of the other laws would actually exist. None of the other laws would even be able to define without zeroth law of thermodynamics, because zeroth law of thermodynamics gives the definition of temperature. Without temperature, you cannot talk about heat, because heat is nothing but temperature multiplied by specific heat multiplied by the mass. Without heat and temperature, you cannot talk about entropy, because entropy is nothing but heat by temperature. Of course, reversible, heat by temperature. You see, so without zeroth law, without temperature, one cannot talk about heat or entropy. So therefore, zeroth law of thermodynamics is very, very important. And what is temperature? Is a temperature is something, I say something hot or something cold, I feel it, or something normal, I touch it and it doesn't feel anything. That's how we define. But remember, why we are feeling hot? Because the temperature of that particular T is higher than the temperature of our body. Or why ice feels cold? Because temperature of the ice is lower than the temperature of our body. That's why it feels cold. So feeling is a relative thing. But how do I know what's the value? How cold it is? If I touch an ice, it will feel cold. If I touch liquid nitrogen, it will feel cold. But which is cold? The liquid nitrogen, of course, you shouldn't even touch, because the temperature is minus 193 degrees centigrade and it will get a frostbite. The point is that these feelings need to be quantified, need to be described in numbers. In order to do that, one needs to find out a scale. So what is zeroth law then? The definition is very simple. When two things, are in thermal equilibrium, for example, A is in thermal equilibrium with C and B is in thermal equilibrium with C, then without even knowing A and B, we can say that A and B are also in thermal equilibrium. So this is a very, when I first studied that, it was difficult for me to understand. So if you replace C by a temperature, a thermometer, then it will become easy. So C is a thermometer. So I am measuring the temperature, thermometer, I am placing it with A, and thermometer gives some signal. I am placing with B, thermometer gives a signal. Both things are same, those signals are by temperature. So therefore A and B are the same temperature. So C, or you can say C is a block of ice, or C is a boiling water. Forget about thermometer. Let's say C is a block of ice and C is a boiling, in two different cases. One case it is a block of ice, another case it is boiling water, let's say. And what I do is that I place a metal on top of C. This metal. So the metal will come to equilibrium with ice and it will have a particular length. And now I put it in a boiling water. And of course it will expand its length. So now I know that, okay, if I put on a boiling water, I get this much length, this much bigger length. If I put on a block of ice, it gives this much length. So which means length can be a measure of temperature. So temperature, you can feel it, but how to quantify it? In order to quantify, you say, okay, I associate a material property. What is the material property I'm talking about here? Length of the metal, of a very specific metal or very specific shape and diameter and everything. So everything is same. If everything is same, then we only talk about the change in length and associate that change in length with the change in temperature. Because we know that boiling water is hot, we know ice is cold. Now I want to know how cold it is. So if I place this metal in front of even colder object, the length will even shrink. So I will know that object is colder than ice. Or if I put on something higher than boiling water, and the length will even more increase. So I will know that, okay, it is higher than even boiling water. So length I am associating with temperature. So see that temperature by itself has definition. We are using a material property to associate temperature with the length. Now, metals do not change so much with heat. So therefore, we use liquid. And thermometer is a famous example of that. Mercury is there, of a very specific, it's a cylindrical object, very specific diameter. So when it expands or contracts in the presence of presence of ice, then we only measure the length. And we don't have to measure the length because length are marked by temperatures. So we think that it is temperature. No, it is just the length that we are measuring. How much it is increasing, that is associated with the temperature, because we already know, we already have calibrated that, okay, this much length means this temperature, this much length means this temperature. So all that is happening when you put a thermometer in your mouth, that liquid is expanding. So we are not measuring temperature, we are measuring material property. Now liquid, which liquid you are going to put? Mercury, water, something else? There can be so many possibilities, and each of them will vary. And more importantly, will each of them vary linearly? That means if I go from ice to water, boiling water, and then from boiling water to if I go to something higher of the same amount, will it increase by the same amount? It may not be. And also it will depend on which liquid it is, because we know that every liquid has a different coefficient of thermal expansion. But fortunately, very dilute gas do not have different coefficient of thermal expansion. If the gas is dilute, it will expand by the same amount in the same range of temperature. So you take a dilute gas and change the temperature, or you can put 2 points, boiling water and ice, and measure it. It will actually be linear. So that means you'll be able to calculate all the intermediate values. And the interesting thing is that if you decrease the temperature, all will go or extrapolate to one particular value. And that value, we call it as absolute zero. Of course, one cannot reach there. We know that. But we can extrapolate that. One can go to a nano-Kelvin temperature. So one can reach there and one can find out that, okay, so that is the point that I take. And then what other point I'm going to take? The other point I'm going to take is, you can take any point, of course, because you need 2 points to draw a straight line. And people normally take, nowadays, conventionally, take the triple point of water, which is very, very specific. This is a phase diagram of water. Triple point, which has a very specific pressure and a very specific temperature. So you know what is the PV value at that point. You know PV value is 0 at 0 Kelvin. Therefore, you know all other points, and you know it is linear. So PV is proportional to temperature. And that finally, I'm not going to detail of that. That finally gives you that PV is proportional to temperature. And once you draw the line, you know the slope, and the slope is nothing but the universal gas constant. Experiment. From experiment, you are getting that. All the major things, Planck's constant, Boltzmann constant, gas constants, those all constants come out of experiment, not theory. They are observations that match with this. And therefore, everything else follows. That is the beauty of every new topic, that there is something in that, one constant that comes out of the observation. Anyway, so among the subjects that I know of course, there are maybe many things that I don't know, but this is the 3 things that I told you, they all come from observations. So PV proportional to T, and we have drawn 2 points. We have drawn the line. Now we fit it and we get R. This is the ideal gas law that we know of, equations of ideal gas. And of course, that works only for the dilute gases, not for concentrated gases, which has interaction. But dilute gases work. So you take a dilute gas and create a gas thermometer, you'll be able to measure the temperature all the way. Boiling water, ice, in between, whatever. Gas expands also very nicely. You get a big differences, you'll be able to measure minutely. So then what we are getting, and why that is happening? Because of zeroth law of thermodynamics, that irrespective of the material, irrespective of whether it's a gas, whether it's a liquid, whether it's a metal or solids, doesn't matter, as long as 2 things are in thermal equilibrium, that property which we call as temperature is going to be same. Because if it could not be same, then we could not use gas thermometer for measuring everything. We can use normal thermometer to measure our body temperature. We can also use normal thermometer to measure water. It does not matter what we are measuring as long as that thermometer is in equilibrium with that material. And that is the beauty. Without that zeroth law, temperature could not be even defined. And without the definition of temperature, could not be defined. How much heat? We only measure by measuring temperature and the specific heat and the mass or volume. So that's why it is zeroth law. That is the beauty of the zeroth law of thermodynamics. It's the most profound law. Anyway, I'll skip this part. So zeroth law summary I have already discussed. Now let us put macroscopic definition. Microscopic definition. Macroscopic you already talked about the temperature, how we are doing it by measuring length and all that. But microscopically, what is temperature? So when something we call as thermal equilibrium, what does it mean? So if you take a cylinder full of gases, the gases are going to move. They are never static, right? Because only at T equal to 0, everything is static. But any other temperature, particles always move. And that movement somehow gives rise to temperature, because if you change the movement, if we increase the temperature, movement is going to change. I'm going to show that, of course. This I'm going to skip in the interest of time, but I can give you the gist. At temperature, Kb is a constant. N is number of molecules is constant. So temperature is nothing but average kinetic energy of the molecule. So if you increase the temperature, average kinetic energy, not kinetic energy of each and every molecule, but on an average, kinetic energy will increase. And we studied that in CBSE 12 standard, that there is a Maxwell-Boltzmann distribution of velocity or speed of particles at a given temperature. So let's say this distribution happens at a low temperature, then this distribution happens at a higher temperature. So when you increase the temperature, it does not mean every gas molecule will increase its velocity. It does not mean that. It only means that the velocities will be redistributed among the particle in such a way that it will form this kind of equations. It will follow this kind of equations. That is the Maxwell-Boltzmann distribution. And somehow this velocities of each particle is giving a sense of temperature. So when you talk about a block of ice, there also particles are vibrating. We talk about a boiling water, there also water molecules are moving. And that movement is indicative of the feel that we get. When you touch and feel it is hot, which means that particles are moving with that velocity. For example, I take my hand, I rub it up. When I rub it, it gets heated, I sense it. Why it is heated? Because all the spin particles now started vibrating into more velocity. Let's say two cars are coming. They have their kinetic energy of the car and they bump into each other. Car stops. Where the energy has gone into? No, cars have become hotter. How it has become hotter? Because those kinetic energy of the car now gone into the vibrational motions, faster vibrational motions of the car particles. And those motions, those velocities are giving a sense of higher temperature. So what is temperature microscopically? It's movement of gas particles. And now I'm going to show you a demo. So I will stop the sharing of this one and I will share something else. Okay, I was sharing the entire screen though. So I could have shared that. Okay, fine. So gases. Is this one or this one? This one is fine. Okay, so this is a very nice demonstration of generally temperature, gases, and all that. Even a small child also will like it. These are all from something called Fate, Colorado. I'm going to. Okay, by the way, do you see my screen here? Can any of you confirm that you are seeing my screen? Okay.
Yes, sir.
Okay, good. So Fate, Colorado, let me go to. You can note it down, especially teachers. It is very useful for teachers. So it is from University of Colorado Boulder, but I did not know when I was there, of course. But they have made lots of simulations or demonstrations for teaching purposes. And once you go there, you can actually get a lot of videos like this, demonstration like this. So I'm showing one of them. So you see there is a very nice pump, and I can put molecules in this with the pump, and you see what is going to happen. Temperature is 300 Kelvin, pressure is 11.9. So pressure comes from heating of the particle on the wall, and temperature comes from the average kinetic energy. Okay. So if I heat the system, temperature is going to increase. As you can see, temperature is now to almost 500. And you see particles are generally, all particles are not moving at the same speed, as you can see, but particles are generally, on an average, is moving faster. That is clearly observable from this, right? So yeah, how do you cool it down? I can cool it down by cooling, actual cooling, or I can cool it down by taking out some particles. Let's take out some particles and see if I'm cooling down or not. No, okay, so I'll cool down it too much. Okay, so okay, let it come to equilibrium. You see, it does not come to equilibrium yet. Now it's going to move and come to equilibrium. Now the temperature is 121. Let me heat to at least 300 Kelvin. Pressure is also increasing. I cannot help that, both are increasing. Now it is going to 250. Let's do it 300. 293, that is fine. Okay, 300. So you can see generally they are moving faster. So now I can cool it down, or I can reduce the pressure? Probably not, because the volume is fixed. If I could increase the volume, I can increase the volume and I can reduce the pressure. See, pressure is 10 now. Let increase the volume again. Oh, pressure is 8 now. Temperature is not changing because I have not changed the, I have not cooled it down. All that I have done is that I have increased the volume. So increasing the volume does not change the temperature, because temperature is average kinetic energy. I cannot change it further. So let's say compress it. My pressure right now it is 8.1, now 19.3. So you see, now I can change the pressure two ways. One is that by decreasing the volume or by decreasing the number. So let us decrease the number and see the pressure is going to change. You see, it's changing both. Now both temperature and pressure is going to change, but pressure is anyway going to change. Okay, so that is one way. And if I cool it down, then what is happening? Then also my pressure and temperature both is going to change. So only pressure, if I want to change, then I have to play with the volume. But if I change with the number, or if I change with the if I change the number, or if I heat it, or in both the processes, I'm going to change both the temperature and the pressure. And that comes from P equal to nRT, right? Only thing that effect of temperature I wanted to show you is it coming from the motions of the particles. So this is what is actual temperature and heat is. Okay. And you know about work and other things. We'll come to that later on. So microscopic understanding of this is extremely important. Now I'll go back to slides. Okay. Gas demo done. So now microscopic motion. Okay, diffusion demo. Okay, diffusion demos I'm going to show you. So this is another system where I can put in some particles. So there are two boxes you can see. So let me put some particles. Mass is 28, so I'm putting like nitrogen particles. So 50 of them I put. Let's say 70, 100. Let's say 100 particles. Where is my center of mass now? Here, correct? Because particles are moving at certain temperature. I can increase the temperature, of course, here, and then particle will move faster. All that, but they're confined. Okay. Now what I'm going to do is that I'm going to just remove the boundary. Now you see the center of mass is coming to the middle because particles are diffusing. Because there is more space, that is entropy. I'll come to that maybe tomorrow. Now reset the divider and let's put some red particles on the right hand side, 100 of them. Okay. Now what is going to happen if I remove the divider? Particles are going to mix and the temperature is okay, I had different temperatures. So let me just make it 300 Kelvin, 300 Kelvin, and you note down the time from now, how much time it is taking. So if it is 300 Kelvin, yeah, it is going to take some time to mix. Okay, let's wait for 2 minutes and see. Eventually it's going to mix. It is not fully mixed, I can see, because the center of masses of both of them will come to the middle. Then only there will be a full mix, right? And of course that will require more time, and more particle would have been better in that case, but it is taking time. It is taking time, correct? So I will change now. So I'll reset the divider, and I will increase the temperature by, up to 500 is maximum. So let's do 500 and remove the divider, and let's see how much time it takes. It should be faster because particles are now moving faster. So it should take lesser time than it took for a lower temperature. Okay. And you can play with that, and you can actually note down the time that it takes and all that, right? Of course, there is a stopwatch, so you can use that, and you can actually measure the time that it takes. Once you remove the divider, you can actually measure. For example, I reset the divider, and let me increase the particle as much as possible because it will be faster. So 200 is the maximum. I can see 200. Okay, remove the divider and start my clock. Okay, 2 at the same time is very difficult to do, but let me do that. Okay, so 500 Kelvin, 200 particles. Let me see how much picosecond it is taking. Although we are looking at in seconds, but particles are moving in picoseconds. That's why it is measured in picoseconds. Okay, so let's see how much time it takes. We'll give it some time. And we can note down, and then we can actually see that whether at a higher temperature it is taking less time or more time and things like that. Okay, so ideally what I'm expecting a full mixing. So full mixing will happen when this center of masses will move the middle, because then only each particles have taken their whole volume, and you see they're coming closer. They will eventually come closer. So let's watch it for some time. Yeah, so this is what happens in reality when you take a glass of water or mix hot water with cold water, or some liquid with something else, or gases. This is what happens in the microscopic level. Our world, what we observe in a macroscopic sense, they are built from those microscopic particles with their motions. See, now they're very, very close, 230, 240 picosecond. So I'm sure that if you now do that with 300 Kelvin temperature, it is going to take you more time. So now I just stopped it because in 270 there's much for the first time. So just take it as an assignment and try to do a different temperature. First time when they're coming close to each other, what is the time that it takes? Make 5 runs of each of them, take an average value for every temperature, and then you can plot it and see for yourself what kind of plot you are doing. And that plot will be mean first passage time calculation for mixing. That will be very, very interesting. Okay, so now let's go back to that one. So how do we measure temperature? Okay, so temperature we talked about as measuring with some material property, right? But how do we measure temperature for a lava, let's say, or the temperature of the sun, for example? Let's say this temperature. Can any of you, normally I ask in the class that can any of you tell me what the temperature of the lava is? Somebody will say 5,000 Kelvin. Somebody will say 2,000 Kelvin. How do we actually know? Is it possible to know? Or do I need a thermometer to go there and measure it? Of course I cannot, right? I cannot even go close to it. So people have figured out how to do that, and that can be done with the help of something called black body radiation. Black body radiation is again in a thermal equilibrium, just like Maxwell boson distribution, blackbody radiation also attains a particular form at a thermal equilibrium, and one can get a measure of temperature. Of course, I will not go into detail of that, but I can tell you by looking at the color of a radiating object, one can find out what the temperature is. For example, a blue color will, the highest frequency will be like 10,000. The outer surface of sun is 5,000 Kelvin, outer surface. Okay, so this lava is almost reddish, so it will be like around 1,000 Kelvin. Our body is not even in the visible range. Our body radiates in the infrared. That we require an infrared camera for that. We are also radiating. So anything that radiates energy will be associated with the blackbody radiation spectrum. That spectrum, if it falls in the visible region, you will be able to see that. And that's what we see from the lava, from the sun, from light, not the LED light though, but the big flashlights, which requires heat to generate the light. So that kind of things. Okay, so difference from some forms of energy, right? So, you know, internal energy is very confusing term. When I was a student, I didn't know what it is, but basically it is nothing but kinetic energy plus potential energy. Okay, so kinetic energy is about movement. If something is static, something is not moving, it has zero kinetic energy. If it moves, it will have kinetic energy half mv square, and that is the temperature. So something is not moving means it is zero temperature. Something is moving, depending on velocity, average kinetic energy will get a temperature. And what is potential energy? Potential energy can be of two types. We normally know about gravitational potential energy. When you are like 7th standard, 8th standard student, you know about gravitational potential energy. But there can be a potential energy of molecular level, which comes from interaction of molecules. So in thermodynamics, both are important. Okay, so you know this typically shows you all molecular interactions and their what energy can be. So typically hydrogen bond energy has certain value, covalent bond has certain value, higher value, and those kind of things, right? So when you tear a paper, you break hydrogen bonds. When you burn a paper, you actually break covalent bond. So therefore, depending on what you are breaking, you're going to get energy out of that accordingly, right? When you break a nucleus, of course, you get much more energy because you are breaking much stronger interaction. So yeah, there are different types of interactions and their potential. I'm not going to go into detail of that. But basically, in chemical reactions, you are going to break a bond. I talked about ATP already, and you are familiar with this kind of energy profiles, energy profile diagram. Reactant goes to product over a transition state, and depending on whether the product is lower than the reactant, we call it exothermic or endothermic, right? So that is very important. But people also talk about E equal to mc square. That means mass energy conversion, which happened during Big Bang. And they ask that wouldn't you get energy from the mass itself? If I have water molecule, mass is this much, how much energy we will get from that? So then I show them this particular periodic table slide from this website, which gives you a periodic table and tells you that which element were generated how. For example, Big Bang, during the Big Bang, hydrogen and helium, I told you, it happened. But look at other ones. For example, lithium, which is yellow color, and little bit of this, pink color also. It requires cosmic ray fission. Beryllium, same. And look at these red ones, ruthenium, rhodium, that requires merging of two neutron stars. That doesn't happen regularly in our Earth. So therefore, on Earth, we do not have mass to energy conversion at all. See, many of us probably believe that when we eat something, we are converting that, that food into energy, and that's how we are actually growing. But just calculate that how much energy is required, how much. So just calculate yourself that we only take 2,000 calories per day. So in a span of 40, 45 years, the energy that you intake, if you convert to the mass, how much mass it will be? It will be only a microgram of mass. Whereas I have, let's say, gained 70, 80 kgs from my birth, but I have only taken an energy which is equivalent to only microgram. And then how it is possible? Because when you put the mass, actually it becomes part of our body. So we take mass from outside and put it inside, and that's how we grow. Those molecules will be part of our body. They don't convert into energy at all. The reaction gets converted to, remember, the reaction gets converted to energy. We get energy out of the reaction, but mass to energy means E equal to mc square, that kind of thing. Like a carbon atom fully annihilating and giving us energy. That does not happen. Okay, work and heat. All of us know the definition of work, force into displacement, right? But heat, a lot of people used to think that heat is a caloric fluid. Somehow it gets into, and then only things will be hotter. Now we already know, right? I already talked about heat being, heat is kind of a measure of like temperature, and then that we get from microscopic motions and stuff like that. I already told you about that. What done is can be easily calculated, so I'm not getting into that. But the heat and the work and the heat, they are related. That came first time by Zoo's paddle wheel experiment. Fantastic experiment it was. So a mass gets dropped by some amount h. So of course we know the changes will be mgh in the potential energy, and therefore an increase in the kinetic energy of this wheel should be a same amount of mgh. But that does not happen. Why? Because some amount of energy is converted to heat, and the difference amount only is converted to the kinetic energy of the wheel. In fact, I think he also measured the temperature of the Niagara Falls, water of the Niagara Falls above and below. Now the temperature below is higher than temperature above, because when it comes, the kinetic energy of this water which is falling down and hitting the ground, the kinetic energy gets converted to the heat, giving rise to an increase in temperature. So that's why the water in the base of the Niagara Falls is higher in temperature than in the top. So which is, tells us that heat is nothing but a conversion of work. So if you drop earlier the cannonball experiment, you drop a cannonball, big ones, it falls to the ground and gets heated up. Car, as I said, bump into each other and gets heated up. So work is getting converted. So they're nothing but the same. So internal energy, which is potential energy or kinetic energy, gets converted to work. So they are equal. There is work and energy are equal, and also work and heat from Joule's experiment are equal. So once more, internal energy and heat are equal from this experiment. Internal energy and work is also related, also in the same way they are similar. So therefore, the first law of thermodynamics is that internal energy can be obtained either by heat or by work. So this is our first law of thermodynamics. So all that it tells us that they are all similar, they are all same. One is an organized conversion of energy, which is work, and one is a disorganized conversion of energy, which is heat. Okay, so again, work is work and heat both are path functions, and in order to understand path function and state function, you need to understand what is exact and inexact differentials, which I'm not going to go into. You can again look at my lectures for that, and there are some discussions that I could have done here, but I'm skipping them in the interest of time because there's so many interesting things to talk about, right? So microscopic definition of heat and work. So what is heat? Temperature is the average kinetic energy, but what is heat? So all of us probably know about particle in a box, quantum mechanical systems, right? So as I told you already, heat and energy are similar, are same. So let's talk about particle distribution in different energy levels. Let's say there are 3 particles in the ground state, 1 particle is in the excited state, and ground state energy is 0. So the overall energy of this particular system is 1, because only 1 particle is there. And let's take another system where there are 1 particle in the energy level 2, 1 particle in energy level 1, and 2 particles in 0. So overall energy is 3, 2 plus 1. So now the heat and work are slightly different. How? So if I work, I'm actually changing the level itself. That means the separation between the level itself increases. So imagine particle in a box, if you have seen it. If you shrink the box, you are doing work on the system, right? Because your volume is decreasing. Then the level go up. Particles will remain the same, but level will go up. And if level goes up, this level which had energy 1 has now energy 2. So by doing work, you are changing the levels. Whereas by putting heat, I don't have that. By putting heat, you are changing the particle distribution itself. You're taking 1 particle here from ground level and putting it in the excited state. I don't have the slide for that. Okay, so let me see if there is any questions at this point. Okay. Okay, fine. There is no question, but if you have any question, okay. So how much time do I have? Because I started a little bit late. So
you can proceed, Doctor. You can.
Okay, fine. I'll just take some more time. Okay, because I'm just going into the second law of thermodynamics. Okay, so first law, we'll talk about heat and work. What is heat? What is work from microscopic level, macroscopic level, and all that, right? And now we are going to go to the most interesting one, which is second law of thermodynamics. So the way I explain first law, or the way people normally explain first law, is that there is no free lunch. That means if you go for lunch, you pay for it. And the way I explain second law of thermodynamics, that you need to tip the restaurant if you want to go for a second time. So that means every time you go, not only that you pay for your lunch, but also you pay a little bit of tip, so that when you go to the next time to the restaurant, you don't feel embarrassed. So this tip, why I am talking about that, why I'm talking about a second time, and why I'm talking about a tip, that probably be clear later on. Now, what is entropy? So so entropy has, it's very mystical. So many things have been said about it. So many quotations are there. So I just read some of the quotations. So it is Einstein's quotation: the classical thermodynamics is only physical theory of the universal content, which I'm convinced that within the applicability of its basic concepts will never be overthrown. That means a solid theory. Second law of thermodynamics has the same degree of truth as the statement that if you throw a tumbler full of water into sea, you cannot get the same tumbler full of water out again. So let's say you take a tumbler full of water and color it green by putting some green color, and you throw it into the sea. Can you get back one bucket, one tumbler full of green water back again from the sea? If you cannot, then the truth in that statement is same as the truth that is there in the second law of thermodynamics. It is as true as that. Another one, heat energy of uniform temperature is the ultimate fate of all energy. Yeah, that is something that I'll probably come to. The power of sunlight, coal, electrical power, water power, winds, tides do all the work of the world. And in the end, all unite to hasten the merry molecular atoms. This is a very beautiful sentence, but in order to understand this, you have to understand the rest of the things that I'll talk about. So it has been suggested that thermodynamics is reversibility. So we know that we are going through an irreversible process, an expansion process of the universe. It is irreversible. It is non-equilibrium, and it is due to cosmological expansion. Why entropy increase is favorable? Forces can be changed. If you give a force, you will get an equal and opposite force. But entropy is asymmetric. It increases with time, it doesn't decrease. And that, Landsberg is saying that it could be due to cosmological expansion. This is much more deeper. Now this one, George Potter, Nobel laureate. I have taken it from a video. So it's a sine qua non, which means that absolutely necessary of the scientific enlightenment, thermodynamics. That means without this, our scientific enlightenment is not going to be possible without knowing thermodynamics. It is as powerful. It is normally taught. I think Professor Raghunathan was saying, right, that physics teaches this thermodynamics and chemistry teaches this thermodynamics. In fact, biology needs thermodynamics. There are books on biological thermodynamics. I gave you examples from Big Bang physics subjects. I give you examples from chemistry, or I can give you examples like gave examples from proteins, biology. So actually in ISER now it is taught as an IDC course, interdisciplinary, because it is so fundamental for every subject. Because engineers study it for making better cars, chemists study it to understand the reactions, physicists study it, for the same other physical processes. So this is a subject that everybody needs, and it's a subject which is very fundamental and very simple. These concepts are difficult, but there are only few equations that you need to know. But the orientation of the mind, it has to be proper so that you can actually appreciate and apply this knowledge when you see it. Okay, so again, changes are everywhere that I talked about, because now changes are associated with the second law. In all processes mentioned above, energy is conserved. Whatever processes I talked about, gas expansion, heat transfer from hot to cold, or if you stretch a rubber band and then it will shrink on its own, a ball bounces back few times and then stops. Everywhere, energy of the system plus surrounding is conserved. But only one direction it happens. So yet the process happens in one direction. An egg falls from your hand, it breaks. Does it ever form back and come to your hand? Never. It happens. If you blow a balloon and then leave it, the air will go out. You never seen air spontaneously goes inside a balloon and inflate it. You have never seen that. Why you have never seen that? Because the first law does not prohibit you from observing that. So forces are equal and opposite. It does not dictate which direction a process should go. So which dictates? Entropy dictates that which direction it will go, from which side to which side. So second law of thermodynamics says that entropy of the system plus surrounding always increases for the process. So we need to look for entropy change of both the system and surrounding. Okay, if you look at separately, then one might decrease, one might increase, but together it must increase. And most importantly, it becomes maximum when the system reaches equilibrium. And then entropy becomes constant. So it increases. Then after reaching equilibrium, it will become constant. So therefore, that's why you see no change. So our universe is not in equilibrium because entropy is always increasing. When it will reach equilibrium, it will no longer, entropy will increase and no longer any change will happen. And when that will happen, think about it, probably I'll tell you in the slides. So these are some examples from Atkins. Ball falls and then bounces and then finally it stops. And why that happens? Because when the ball falls, it hits the ground. So now ground hits back not with equal and opposite force because it's not an elastic collision. So some of the energy escapes into the floor particles, and that floor particle will hit the other floor particle. Then that will hit the other floor particle. So now these floor particles will now distribute the energy among itself, and it will not get it back again. Because it does not get it back again, it cannot hit the ball with the same force that the ball hit with that. Okay, so again, reforming the egg. I have these demos, I think, but it's okay. I'll just skip it. Let me see this one. So this is a process where spontaneously air came inside into the balloon and inflated it. Do you think it is possible? Do you think this is possible, where ink is getting disappeared from a mixture and going to the dropper? Or do you think this is possible, where pen comes from nowhere and arranges itself? So in all of that, things are run in the backward in time. So we have taken the movie and we ran it backward. So these things cannot happen in our physical universe. Now, this is also a similar example of mixing. So things mixed. Do you think that it is possible? No, right? So it has run backward. Now tell me, like normally asked in the class, that since you know all those things are run backward in time, can you tell me whether this movie is backward in time or forward in time? If you can identify clearly that it is backward in time, then you know that it cannot happen in real universe. If you can identify it is forward in time, then you know that it can happen in the universe. But I think you cannot identify, right? You cannot identify if the movie is forward or backward, right? That means this is happening in equilibrium. Only when things are happening in equilibrium, then only you know. You don't know whether the movie has run backward or forward in time. So point is that time arrow and entropy arrow is the same. Entropy increases with time. Whatever entropy of the universe is today, it was less yesterday, even lesser day before yesterday. And if you go back, it started with the Big Bang. I already showed you this, right? And the interesting thing is that we are here today, so tomorrow's entropy will be higher, day after tomorrow will be even higher, next day will be even higher, but when it will end? When it will become maximum. But when it will become maximum? You know that I already told you, right, that distribution of energy needs to be flatter in order for the entropy to increase. So if you have a piece of coal, it has to be burned, because piece of coal has a concentrated energy. Or a petrol has a concentrated energy. Our body has a concentrated energy. A piece of paper has a concentrated energy. Any construction that you see has a concentrated energy. So when those energies are going to be distributed in converted to heat, then only it will become maximum, where no longer energy is stored anywhere. That means no life form, no chemicals, no material, nothing. And entropy increases also with expansion. So temperature becomes cooler and cooler. So at the time of Big Bang, the temperature was 31, 32 Kelvin. Right now, the background radiation temperature is 2.7 Kelvin, very close to absolute zero, but not absolute zero. So, and universe is still expanding. So the future, the end, the maximum entropy situation is when there is no longer going to be any material form, anywhere concentrated energy, and it will be expanded so much that the temperature has cooled down to absolute zero, because zero is not possible. So very close to absolute zero. So very cold heat bath is the final future of our universe. It is sad, but it is the fact. And that's what it is told in this particular quotation, that the power of sunlight, cold, electrical, water power, wind, and all that, and in the end, all unite to hasten the very molecular dance. So basically, at the end, it will be just even molecule, only atoms and molecules, if it doesn't convert to energy. That is so. At the end, it will be just the heat and cold heat bath, which is just molecular dance. Means what? Movement of molecules. And temperature cold means what? That average velocities also will be less. So very low velocity movement of atoms and molecules. That's it. Atoms, basically. That is the end. Okay, so I think that, okay, now Now I have to go from here to the formal definition of entropy. So I will stop here. Maybe we'll continue from here because there's more than 1.5 hours. And if I do a little bit more, then you guys will be terribly bored. So I'll stop here and I will just now ask you for questions if you have anything. Then we can discuss that. And tomorrow we will continue from here. Does it sound all right, Professor Velachery?
Yes, Dr. Arnab. It was very wonderful the way in which you have introduced the basic things about thermodynamics. It was very interesting with a lot of day-to-day life examples you had given. I think the students must have definitely enjoyed. Dear students, if you have any questions, now it is the time for you to get it clarified by the resource person, Dr. Arnab. Don't miss this chance.
And also the thing is that, you know, if you are hesitant, you can also go to NPTEL lectures or subscribe to it, and you will get more detail of each of these in those lectures are all free. Only for exam you need money, but if you don't want to give exam, it will be free. Okay, with that so I invite you to ask questions if you have.
Students, even if you do not want to switch on your video and ask the question, you can put the question in the chat box. We can read it out for
he
you.
was asking 1042 PTs. Siddharth, I think he was asking something. Yes, Siddharth.
Yes, sir. So if plasma is stored in a magnetic field, will the plasma still lose its temperature, sir? Will the plasma cool down over time?
So everything will cool down over time. If the situation is left to itself, that is the beauty of entropy. If it is left to itself, then it has to eventually cool down. Nothing will remain like this forever. So when you are radiating heat, if you can manage something in an isolated environment where there is no exchange of energy possible, then it will remain in that energy. But if it is not isolated, then it is going to radiate energy and cool down.
Okay, sir.
Hello?
Dear students, any other question, ma? Or else you can do one thing, you note down the questions. Tomorrow is also, sir is going to be there with us.
Yeah.
And then we can have the interactive session. Okay.
Yeah, so in fact, you can ask anonymously also. Professor Velachery, is it possible to have a poll with this Google Meet? Like poll kind of thing, is it possible?
In this, actually, we haven't tried that, sir.
Okay. No problem. So I do it now normally for a large class to take a poll because the anonymous can say things. So sometimes.
No, we'll be having the feedback tomorrow. We'll give the questions over there, not directly on the platform. Okay. Let me see what I can do. Tomorrow, if it is possible, I can do that.
Okay.
Anand.
Hello.
Anand.
One small request from the participants. If it is all right, you can unmute your video and let us take a screenshot. All the participants. And if it is possible, you can also take screenshot because in my screen, some persons will be coming in your screen, some other persons will be visible.
Correct.
Okay.
Yeah, that will be wonderful to look at faces of the student.
Yeah, definitely.
Normally we miss that in our online lectures, right? That is, I really love to see. Normally I teach a class of 250 students.
Okay.
So full of students in the class.
Abhinaya, Varun, all the students, time come into video mode. Kalevani, Shankaranarayanan. Raji, could you please take the screenshot, ma, because I am unable to. Ma'am, now it's no, ma'am. SL, ma'am. Now a little bit. Yes, ma'am. Okay. Raji, please take, ma.
Yes, madam. Yes, madam.
Okay. Thank you all. And Mr. Shankar, now I think you can stop the YouTube live streaming. And for the participants, the attendance link is posted in the chat box. You can fill it up. And Professor Saroja. Okay, Rangasam, you can carry on.
Just a thank you is a mighty powerful prayer. Says it all.
Hello.
Now I would like to call upon our senior Ms. T. Saroja, Associate Professor, Guru Nanak College, for the vote of thanks. Ma'am.
I thank Dr. Arnav Mukherjee for his wonderful and motivational lecture on introduction to thermodynamics. Actually, sir, as you know, normally our students, they don't show much interest on physical chemistry. And thermodynamics, they think it's a dry subject. But since it involves a lot of mathematics and derivations. But I think today you've taken the subject in an interesting and lively manner by giving a number of examples. And all your slides are beautifully shown. So I'm sure that your talk that really inspired our students' interest in physical chemistry and kindled their interest to work more for physical chemistry. I should say it was really a motivational speech. And I'm sure all the students have been benefited out of your talk. So I thank you, sir, once again for your valuable speech. I thank all the participants for today's webinar. Thank you once again.
Thank you.
Thank you, ma'am. Continuity gives us
so much. Yes. Are you talking now?
Anand, please.
Yes, sir. Continuity gives us roots. Like this, we are going to continue this webinar to tomorrow here at same time. Stay tuned, stay ready.
I think all of them can leave, madam.
Yes. Dr. Adam, thank you so much. We will be tomorrow at the same time.
And same link, right? Is the same link?
Yeah, same time. Same, the link, Google Meet link remains the same. Yeah.
Oh,
same link only. Thank you. Thanks a lot.
Thank you very much. Thank you. Bye bye. We'll see you tomorrow.
Yeah. Students, you can follow the attendance link and submit and you can leave.
Thank you, ma'am.
I request only the staff members to be present here.
Thank you, ma'am.
ஸ்டாப் பண்ணிட்டீங்கல்ல? நான் அப்பவே சொன்னேன், ஐயோ நான் பாட்டுக்கு பேசிட்டு இருக்கேன் போங்க. ஓகே.